Welcome back to another exciting chemistry lesson. In the previous lesson, we learned about electromagnetic radiation that has a dual properties of wave-like and particle-like. And we look at wave in terms of C equal to frequency times lambda. And then we also look at in terms of their relationship when we try to compare the relationship between frequency and lambda. And we realize it has an inverse relationship, okay? Now today we are going to tie it to another equation, and that is E, which is energy, equal to Planck constant times frequency. But this right here, V is equal to what? Well, that is the speed of light over lambda. So in a way, we can think of this as C over lambda. Now, what does that tell you about the relationship between the three variables, energy, frequency, and lambda? For example, if we have frequency go up, guess what happened? Energy also go up. But for lambda, on the other hand, it go down. And this is illustrated in this equation right here. So as you can see, gamma, think of the Hulk, right? Think of all this gamma radiation, okay, the dangerous gamma radiation. And then think of something like radio waves or something like microwave. Those are very safe. So the more energy it has, the more dangerous it's going to be. It's going to cause cancer and all of other medical problems. And that's why we are pretty much safe when we listen to our radios. And as you can see, for radio wave, look at the wavelength, it's a lot larger, right? So for the larger radio wavelengths, guess what happened? Frequency decrease as well as energy decrease. So make sure you understand the relationship between variables by looking at this formula right here, okay? So that's very important, and that will be part of a lot of our, and this type of relationship will usually ask through multiple choice as well. And this type of relationship is usually asked through multiple choice on your AP Chem test. So as you can see in this equation, we look at electromagnetic radiation in terms of photons. So this is particle-like, okay? Before we look at in terms of wave-like. Now we combine it and look at in terms of particle-like property. And that's why we look at photon. And now with that information, let's go back. The Planck constant again is a constant value. It does not change. So that's very important. And then one most important thing we have to remember is the unit is in joule and second, joule times second. So by understanding the unit, sometimes we solve the whole entire problem wrong because we have the wrong unit. It has to be joule and second. Now let's solve a problem. We have a molecule ozone O3 absorb a photon. So we're looking at particle-like with a frequency of 1.2 times 10 to the 15 per second, right? Again, frequency is per second. Determine how much energy absorbed by this particular ozone per photon. So let's solve this problem. So first of all, what do we have? First we look for energy, so that's E, assign the variable, and frequency is V. So which equation give us E and V? Well, in this case, we have E equal to HV. Remember, E is energy, V is frequency, and this is a constant, so we don't really care about it. It is a variable. It dictates what is the unit we're going to use. Well, for Planck constant is joule times second, so we have second, that's good. And now for the unit energy, we are looking for joule, so that's pretty good. So in this case, we plug it in. E is equal to, just plug it in, we have 6.63 times 10 to the what? Negative 34. And notice how I don't have my unit in here, okay? I don't want to write too many things. It got confusing. And then for frequency, what do we have? 1.2 times 10 to the 15. Now, just to show you in terms of unit, we have joule times second multiplied by 1 over second. Look what happened. Second cancel out and give us joule. So you can do this without plugging the number. So let's plug in our calculator, okay? So 6.63 e negative 34 times 1.2 e to 15. And that answer turned out to be 7.96 times 10 to the negative 19. And this is joule per photon. Okay? And that is our answer. Okay, now let's go in and look at how much energy is absorbed per 1 mole of ozone. So now we'll have photon. So remember, one of the most challenging about particles or moles and atoms is that all of them relate to this one factor, and that is the Avogadro number. When we talk about in terms of mole, we are talking about 6.02 times 10 to the 23rd particles, right? Represented particles to be exact, per 1 mole. And that's something that's really tricky for our student. So whenever we talk about mole and some kind of particles, atoms, ions, whatever it is, it doesn't really matter. The relationship between that 1 mole and that whatever represented particle is always the Avogadro number. So let's solve this problem. We have, what is this? We have this per photon. We have 7.1. So we have per photon, we have 7.96, right, times 10 to negative 19. So in this case, remember, this is joule per photon. So how do we get rid of photon? Well, based on the Avogadro number, 6.02 times 10 to the 23rd photon is equal to 1 mole. That's why we're looking per mole right there. So if we do this and continue solving for it, what do we have? So our answer turned out to be 4.79 times 10 to the 5th power. And that is what? Notice how we have photon cancel out. And that is joule per mole. Okay? But our answer is asking in for kilojoule. So we had to go to the extra steps. Okay? We had to go to the extra step over here. And what do we have? We had to multiply that. What is that going to be? How do you convert joule to kilojoule? And that's pretty easy. Remember, what do we know about the relationship between joule and kilojoule? Well, 1 kilojoule is equal to 10 to the 3rd joule. So we have 10 to the 3rd joule, 1 kilojoule. And as always, we can now cancel out joule. What does that turn out to be? Well, this is divided, so we can subtract, right? So in a way, we can think of this as 4.79 times 10 to the 5th minus 3. What's that going to be? 2. So our answer is 4.79 times 10 to the 2nd kilojoule per mole. Or you can write this as 479 kilojoule per mole. Your choice, okay? Now, to break an oxygen and oxygen bond, it requires a minimum of 380 kilojoule per mole. Does it have enough energy to break the bond? Well, look at this. How much do we have over here? We have 479 kilojoule per mole. So therefore, the answer is yes, we have a lot. That will have enough energy to break the bond. And as always, you need to remember this equation. Even though it's given to you on your periodic table, know it. It will save you a lot of time. And also, if you have any question, take a picture of your work, put it in Google Drive, and share it in the forum, and we will help you from there. And we'll see you next time on another chemistry video lesson.